Hello everyone, welcome to the non-relativistic holography parallel session of this conference. For the first talk, we have Jelle Hartong, who is also the convener of this session, who is going to discuss non-Lorentzian geometry and string theory.
Great, thank you very much, welcome to this parallel session. So I'll kick off by giving you somewhere in the middle between a sales pitch and a research talk on non-Lorentzian geometry, and then the second part of the talk, some non-relativistic string theory. So just to motivate this, let me introduce a number of questions that I think motivate some of this research. This is not an exhaustive list. So to start somewhere familiar, it's very well known that if you take the non-relativistic approximation of GR and you assume weak fields, then of course you get Newtonian gravity. But what has been realized relatively recently is that this non-relativistic approximation doesn't have to assume weak fields. And if you drop that assumption, you get something quite a bit more general, which is what I call non-relativistic gravity. So this is a theory that you can get systematically from GR by expanding it in inverse powers of speed of light. I'll explain later exactly how that works. And this is a much richer theory than it's a geometrical theory. It's diffeomorphism invariant. You can define it off shell. There's a Lagrangian for it. It's really sort of, you can treat that theory on its own merits and see what you can do with it. And of course you can correct it. So you can add what you might call post-Newtonian corrections, and you get more and more complicated theories that approximate GR better and better as you go along. And the geometry that underlies this is some particular version of non-Lorentzian geometry called Newton-Cartan geometry, and that we'll come to talk about in some detail later. And then you can ask, can I couple this background to a quantum system, a quantum mechanical system, so like quantum mechanics, not really quantum field theory. And if I treat that quantum mechanical system quantum mechanically, it can back react on that geometry. And what's the complete theory of that? And I think the answer is we don't know. And that theory is what I mean when I say non-relativistic quantum gravity. That would have to sort of describe that sort of self-consistently. And then you can ask, suppose we understand that theory, does that teach us something important about the relativistic theory of quantum gravity? It almost has to, you would think, because it should come as a limit. And maybe you can try to ask, is that theory a string theory? Could it be a string theory? So that's part of the motivation to look at non-relativistic strings. More on string theory, you can take, it's obviously a very complicated theory, so it's interesting to look at limits of it. And a lot of these limits involve some version of non-Lorentzian geometry, as we will see. And whereas there's growing evidence that if you take these limits sufficiently carefully, that things like holographic dualities may well still be true to some degree in the limit. So you can really ask, is there something like a holographic dual of both non-relativistic string theory versus a non-relativistic quantum field theory or quantum mechanics. And then more generally, you can ask, now that you've introduced non-relativistic strings, you will see that they couple to a target space that is no longer Lorentzian. It turns out that you can define many of these kinds of string theories, and we understand these geometries now sufficiently well that you can study them sort of on their own merit, no longer as limits. And then you can try to use those to see if you can cook up interesting holographic dualities, because these theories often have both closed and open strings, and you might expect that there is again some kind of duality. So, and then I should also mention that independently of all of this, non-Lorentzian geometry appears very generically in low energy physics, condensed matter physics, fluid dynamics, if you want to couple it, because these systems are typically not Lorentz invariant. So if you want to couple those to a curved geometry, it's almost always some non-Lorentzian geometry. So there's many reasons why people study these things, and here's just some of the reasons why people do that. So I want to start by giving you some flavor of what these geometries actually are. Then talk a bit about this non-relativistic gravity that I mentioned, and some hints of some kind of fluid gravity correspondence. And then this last part of the talk, I will talk about open and closed non-relativistic strings. Okay. So the main idea, as you know, in general relativity, you have a metric that is invertible. In non-Lorentzian geometries, you typically don't have a metric that is invertible. So you have to do something different. And so we use a Vielbein formulation. And there's two classes of Vielbeins in non-Lorentzian geometry, usually called tau and E. The tau Vielbeins, they carry, in this case, capital A index. And that's a Lorentz index. So there's together they transform under some group G that I leave unspecified. But I assume that inside G I have at least a Lorentz subgroup. So this is in some vector representation of SO1, P. These we call you could say the Lorentzian Vielbeine. And then you have spatial Vielbeine that transform under SOD minus P. And the whole set of Vielbeine has to form a complete basis everywhere on the manifold, so they're nowhere vanishing, and you can span the whole tangent space with these Vielbeine. So you can also invert them, and that's really what sort of replaces this notion of inverting a metric in non-Lorentzian geometry. And then the kind of non-Lorentzian geometry depends really very heavily on what you choose for G. And there are many options, as you will see in a minute. But typically it's some contraction of the Lorentz group or some subgroup of the Lorentz group, depending on the physical context. Now, what makes it a little bit more difficult to classify, because if this was everything, you could classify it quite easily just based on what G is. But almost all physical situations where you encounter non-Lorentzian geometry, you get more than just these Vielbeine. And one way to see this is, and it will become more manifest later, if you expand in 1 over C, say the metric, then at leading order you get these Vielbeine, but then you have subleading fields. And these subleading fields are also very important, and you could think of them as sort of gauge fields that live on the manifold with this sort of metric structure. But different from what would happen in GR, these gauge fields also transform under this group G. And there's an example here. So this is what leads to many notions of different non-Lorentzian geometries, because this can be done in many different ways. So Newton-Cartan geometry, then you would just have one tau. So that's it's called the clock 1 form, and everybody else is spatial. And then there is an additional field that's called M. Physically, this makes a lot of sense, because if you think about these fields in terms of, you couple some field theory to it, you can vary these fields and you can look at the responses. So the response to tau would be the energy current, and the response to E would give you the momentum. And then the response to M will be a mass current, which is rigorously conserved in a typical non-relativistic theory. So you need an extra sort of source to account for the mass current. So that's one way to understand that it has to be there. Now, in Newton-Cartan geometry, this group G acts in the following way. Time is absolute, so the time-like Vielbein doesn't change. Then you have rotations acting on the spatial ones. This is a generic, that always happens. But then E goes into tau. That's what we call a local Galilean boost. But unlike in a relativistic context, tau does not go into E. So that sort of symmetry is broken here. But you see that this lambda also appears in the transformation of M. So M also transforms under G, under this local Galilean boost. But it also has its own gauge transformation, right? So it transforms like a connection, U1 connection 1, 4. And then you can couple theories to this kind of background and require that these theories are invariant under these symmetries, and you get non-relativistic physics straight off the bat. Okay. So other options are, so Newton-Cartan, as I said, you transform tau and E in this way. You can also do sort of the opposite of this. So rather than shifting E into tau, you shift tau into E. That is what we call Carroll geometry. You may have heard a lot about Carroll geometry recently, because it plays an important role Whenever you see a null hypersurface, or in particular asymptotically flat spaces have null hypersurfaces of future null infinity, and they're described by these Carroll geometries. So there you have only rotations acting on the space-like Vielbeiner. So here space is absolute, because it doesn't go into time. So in Newton-Cartan time is absolute, and Carroll space is absolute. And then there is sort of the intersection of these, which is Aristotelian geometry, where both time and space are absolute. And this is an important geometry that you use whenever the system that you're coupling to a background doesn't have any boost symmetry. And this can be quite common in condensed matter systems or field theories, fluids, I mean. Okay, then once you have these Vielbeiner, you want to introduce a connection and a curvature and all that. This is a bit of a long story. It's a little bit more complicated than in GR, but essentially it goes via a very similar procedure. One way of doing it is to introduce Vielbein postulates. So you build a derivative that is covariant with respect to all of the gauge transformations, so diffeomorphisms, your lambda and lambda AB transformations, and then you build a big connection that has an affine connection and a boost connection and a rotation connection, acts on these Vielbein, and you set that to 0. That's your Vielbein postulate. And then from there you can build all the curvatures that you need. And then typically what you get is a connection, like an affine connection that looks like this. But you also have, and this is sort of case specific, you will in general have some tensor here that makes this one non-symmetric. So very generically, you may have heard this, that in non-Lorentzian geometry typically you have torsion. So this is not symmetric, so there's torsion in there. And this torsion really comes from just, for example, in Newton-Cartan, if I take the exterior derivative of tau, that is a tensor that I can put that is antisymmetric, and that gives you what we call intrinsic torsion. So intrinsic torsion is torsion that you can build using the geometric data. It's not some additional field that you put in. It comes directly from the Vielbeiner themselves. Okay. So where do we encounter these? Again, this is a non-exhaustive list. But I already mentioned that in approximations of GR, if you do post-Newtonian corrections, then that is based on Newton-Cartan geometry at leading order. The way I sort of stumbled upon these things originally was by looking at boundaries of spacetimes that are not ADS, so like Penrose type boundaries or generalizations of Penrose type boundaries. And I think that generically, if you can define the boundary of a spacetime, even if the spacetime is a solution of Einstein's theory, and so the bulk is described by Lorentzian geometry, the boundary won't be. So generically, the boundary is some non-Lorentzian object. So that's true for Lifshitz spacetimes, Schrödinger spacetimes, and asymptotically flat spacetimes. You also encounter these things whenever something funny happens. So, for example, a null hypersurface, if you ask what is the intrinsic geometry on a null hypersurface, it turns out to be something that is Carolian, so like a black hole horizon, would be described by Carroll geometry. You can look at singularities in GR, referred to a talk by Gerben earlier this week. Close to singularities, like in the Schwarzschild geometry, if you zoom in on the singularity, you can show again that Carroll geometry emerges close to that singularity. So in the Schwarzschild metric, you find Carroll geometry at the singularity, at the horizon, and at infinity. So it's really quite omnipresent in some sense. In low energy field theories, as I've mentioned, you typically encounter non-Lorentzian geometries, limits of string theory, or say more on this later. In cosmology, you can encounter Carroll geometry, because Carroll is in some sense an ultra-local limit, so different points in space are causally disconnected from their neighbors. So if you're on super Hubble scales, then this is the kind of causal structure that you expect. Horzava-Lifshitz gravity, if you can formulate that in a diffeomorphism invariant way, if you use Aristotelian geometry. Okay. But there are many other instances where you encounter these things. Okay, so let me switch to the first topic, which is non-relativistic gravity. And I already mentioned in the beginning that it's a textbook result that if you take GR and you do a non-relativistic approximation, you see on weak fields, you get Newtonian gravity. So I want to do that a bit more systematically and covariantly, and I don't want to assume weak fields. So we have to somehow write the Einstein-Hilbert action in a way that the speed of light is made manifest. So the way we do that is as follows. The first step is we change the variables of theory. We're not going to work with a metric. Instead, we're going to work with Vielbeine. So T is a time-like Vielbeine, and pi are all the space-like Vielbeine put together into one symmetric tensor. So this has 1, 0 eigenvalue. So the signature contains 1, 0. And then, so this you can always do. So we put a c-squared here such that the one form T has dimensions of time. And then the big assumption is that you can now Taylor expand these variables T and pi. This may not always be true. There may be coordinate systems where the speed of light isn't analytic or something like this. But this is the assumption that is always made in this here. And notice that I've only included even powers, but that was really, in some sense, an over-restriction. You should really include the odd powers. But it turns out that especially at low orders, these odd powers either can be shown to be pure gauge or they're simply zero. So for example, in post-Newtonian corrections, the odd powers only start to appear later, and they describe things like retardation effects. So if you have time, so if you have dynamical processes like gravitational wave production, you really need to include the odd powers. But that's not what I'm going to be doing here, so it's sufficiently general to include only even powers now. And then it turns out that in order to so I already mentioned that the connection in Newton-Cartan geometry is not the usual Levi-Civita connection. So you want to start with a connection that when you 1 over c expanded immediately gives you the connection that you want at leading order, which is the Newton-Cartan connection. So for that reason, we switched from the Levi-Civita connection down to this somewhat exotic connection. You can just do that. I mean, these are dependent connections. They're not independent fields. So in some sense, it's free to use any connection that you like. And if you do this, then the Einstein-Hilbert action becomes this object here. And now you just expand it using these, so you expand it off shell using these Taylor expansions. And what you get is a cascade of Lagrangians at lower powers of c. So at highest power you get some leading order theory, a next to leading order theory, etc., etc., etc. It turns out the leading order theory is not really, it's more like a constraint. You shouldn't really think of it as a theory on its own. It just tells us that the clock 1 form has to obey this Frobenius condition, which means that there is a foliation of absolute time slices in your Newton-Cartan geometry. So GR always fixes this. There's no way around this. And then, if I go back, so in here, when you have, so this will depend on leading order fields. So there are some equations of motion for these leading order fields. The next to leading order Lagrangian reproduces these leading order equations of motion by varying this with respect to the next to leading order fields. So the equations of motion are repeated. So the next to leading order Lagrangian knows about all the equations of motions of the Lagrangians before, plus new ones. So that's an important structure that you can prove always persists. And then this next to leading order theory is what I call non-relativistic gravity. So if you write the equations of motion of this theory, as a special case, it contains Newtonian gravity, written covariantly. That's called Newton-Cartan gravity. But it now contains more because we didn't assume weak fields. And weak field would mean that the leading order geometry described by tau and h would be flat. Whereas here, it doesn't have to be flat. In particular, if you add a negative cosmological constant, you can construct this solution that we call non-relativistic ADS. And if you ask what are the killing vectors of this geometry, then it turns out they form what's called the Galilean conformal algebra. So that's literally this large speed of light contraction of the relativistic conformal algebra. And this has a Penrose-like boundary at R is 0. So you can make that quite vigorously well defined. And that boundary you can show is again Newton-Cartan. It's a conformal class of Newton-Cartan geometries that appears on that boundary. And then you can ask, well, can I do some kind of fluid gravity like you do in ADS-CFT? So what would you do in ADS? You would you would then create a planar ADS black brane solution. So here it's not going to be black, but we'll call it some kind of planar excitation. So this is the most general solution. A is just a constant. D is the number of space-time dimensions. And you can show that if you assume that this planar excitation respects all the symmetries of the boundary, so translation symmetries and rotation symmetries, this is the most general solution. And then what you do in fluid gravity is you give it a boost. So in that case, you would give it a Lorentz boost to give it some velocity. So here you would perform a Galilean boost, which is an asymptotic symmetry, so it doesn't change the sources, the boundary geometry, but it changes the VEF, if you like. So you get now an energy momentum tensor. So rho is a constant that's proportional to A. And if you go through the whole process of computing the boundary energy momentum tensor, this is the end result. Now you may stare at this for a while, thank you, and realize that this is a Galilean fluid, but it has one funny property, namely that the momentum vanishes. So we call it a massless Galilean fluid. Oh, sorry, yes, this should be T up, I down. Yeah, well spotted. Yeah, thanks. So it's the charge of the momentum, yeah. So that's zero. That's a bit unusual, but yeah, it is what it is. Now you can, but this is sort of a proof of principle. You can now sort of change the vacuum by playing around with this ansatz here and add suitable matter, and then, well, this still needs to be confirmed, but then I would expect that you can get an actual massive or Barkman Galilean fluid on the boundary, which is a Barkman fluid is the kind of fluid that we see every day. Like this is the Navier-Stokes type equation fluid. So it will be quite interesting to sort of generalize the setup so that we can also account for those kinds of fluids.
So you said you would be able to do that if you were to consider a different gravitational solution?
Yes, yeah. So you have to include some dynamical critical exponent here.
But it makes sense, right, that you get massless Galilean since you have this control?
Yeah, no, it makes total sense. This is no surprise at all. But I just wanted to highlight that it is not restricted to just this class of fluids if you start with a different vacuum. Okay, I'm going way slower than I had expected, so I only now come to the topic of strings, and I have 5 minutes left, so I'll try to be brief. So you can now ask, is there a string whose beta functions give me this non-relativistic gravity theory? And it turns out that's not so easy, because in order to find a non-relativistic limit of the string, I need some... Normally, if you take a non-relativistic limit, you have a rest mass, and then you have something that is small compared to that rest mass, so you can call it a non-relativistic V over C type expansion. So you need to give this string a rest mass, and the way to do that is to wrap it. So you wrap it around a circle. So you need to add a circle to the target space. So basically what you need in order to do a non-relativistic approximation of a string is you take a Newton-Cartan target space and add a circle to it. And let the string wrap that circle, and then it has a mass, and then you can define a non-relativistic expansion. And this addition of this act of adding a circle to the target space changes the geometry to what we call string Newton-Cartan geometry. And in that case, you have two of these taus. So you have a tau 0, which is the one that we had, the one that describes time. But now you also have a tau 1, which is sort of the one that takes care of this circle. Then, thanks. Then you can, then the target space, now it has a circle. So the time and the circle form a cylinder, and then you have transverse directions to that cylinder. And these transverse directions form your standard Riemannian geometry. And then the whole thing can be thought of as a fibration of Riemann spaces fibered over the base, which is the cylinder. And if the string does not fluctuate, the world sheet of the string is mapped into that cylinder, one-to-one. And when it starts to fluctuate, you assume that the pullback metric on that cylinder is always Lorentzian. So that's the basic setup of non-relativistic string theory. And then you can show that you can write down sort of, this is the number go-to action for a string in a string Newton-Cartan target space that also has like a B field in it. That for technical reasons here is called M. So this is, in a nutshell, the the Lagrangian of non-relativistic string theory. You can add a dilettante to this as well, but at the classical level, this would be all you have. Then you can show that the spectrum is non-relativistic, but in the interest of time, I will skip the rest of the comments here. Just wanted to highlight that you can also do open strings. For the open string, you have to be a little bit careful, because if you have this is a bosonic string theory, so if you have a D25 brane, the open string endpoint is a massless particle. It's very difficult to 1/C expand massless particles. But if you take a D24 brane, the endpoint becomes a massive particle, and those you can expand very straightforwardly. And also, the open string needs to wrap this circle in order to give it a mass. That circle needs to be longitudinal to the string. The string is transverse to the brane, so that circle has to be transverse to the brane. So the highest dimension of a brane that you can have is 24 for a D brane in non-relativistic string theory. The critical dimension is still 26, hasn't changed. Okay, then to make a long story short, you can then ask what are the world volume fields on that brane and what kind of theory do they describe. And it turns out that they describe, so in the relativistic case, you would get the Dirac-Bohr-Infeld action. So now you're going to get a non-relativistic version of that. So you might ask, what on earth is that? It turns out that this is the answer. But to give you an idea of what that is, if you expand it in 1/T, which is the non-relativistic string tension, this is like your alpha prime, then you get this action here. And this is what we call Galilean electrodynamics. So this is a Galilean invariant version of Maxwell's theory, if you like. And this is just a nonlinear version of that. So you have D-branes, they have this kind of theory living on it. I think if you were to take multiple D-branes, then you get non-abelian versions of this. Okay, since I'm out of time, I'll stop here. Thank you for your attention.
Questions?
Both regarding non-relativistic gravity theories and field theories and a possible duality between them. Is it known whether there are any theories or models of all of these things which are consistent but are not a non-relativistic limit of a Lorentzian theory? And is there even a way to tell?
Yeah, I think it's fair to say that all the non-Lorentzian string theories that we have studied so far are in one way or another obtainable from ordinary string theory. Whether this is by expansion or null reduction or dualities or other limits. So one thing that I think is interesting is to, that wouldn't come from string theory in any obvious way, is to take like a string version of Aristotelian geometry and to then compute the beta functions of that and to see if you can make contact with, say, Holjava-Lipschitz gravity. But this is speculation. Nobody has done it. People have computed beta functions for the non-relativistic string that I showed you, and that gives non-relativistic gravity, with the exception that now it's string Newton-Cartan geometry, not the ordinary Newton-Cartan geometry. But maybe if you, because you have a circle, you could do a Kaluza-Klein reduction. You could make contact with the standard non-relativistic gravity that I mentioned earlier. But that's, again, hasn't been worked out. So, yeah, at the moment I don't know. But we have quite on the topic of holography, we have quite a lot of hints now that, and you will hear more about this probably in the next talk. One thing that I didn't mention, when I introduced this string Newton-Cartan geometry, the cylinder is a Lorentzian submanifold of the target space. So it has its own speed of light. And that's the one I call C tilde. So if you're a non-relativistic person, you see speed of light, you want to do something with it. So you can send it to infinity, see what happens. And actually that gives you a string theory. This string theory, if you write it in polynomial form, still has a CFT on the worldsheet. That string theory no longer has a CFT on the worldsheet. It's a sigma model that's first order in time derivatives. And that is something we call the spin matrix theory. And that you can get by if you go to alias 5 crosses 5 and you zoom in on near BPS bounds of the N4 superennials, and you do that on in the bulk, you get exactly this class of strings. And then the duality seems to still work. So you have this is probably our best example of a sort of non-relativistic duality between strings and some kind of field theory, which are these spin matrix strings.
Unfortunately, we have to move on to the next talk. So let's thank Jelle again.